So let's do an example from scratch. The example I want to do is the following. I want to look at x prime equals 1, negative 2, 1, 3 times x. Okay? Now we know the deal, I hope. We want to look at the characteristic polynomial, which is, of course, the determinant of 1 minus lambda, negative 2, 1, 3 minus lambda. And this should be automatic. This is the product of 1 minus lambda and 3 minus lambda minus negative 2. So that's plus 2. Expanding this out, we get lambda squared minus 4 lambda plus 3 plus 2, which is, of course, lambda squared minus 4 lambda plus 5. All right? Now, you use the quadratic formula, and you should do this if you're confused. You should just test yourself. Lambda, the eigenvalues are going to be 2 plus or minus I. You can check that yourself. Okay? Just use quadratic formula. Okay. Next, what I'm going to do is compute eigenvalue vectors, okay, associated to one or the other of this complex conjugate pair. I'm going to choose lambda equal to 2 plus I. So lambda will be 2 plus I. And I'm going to find an associated eigenvector. How? Well, I'm going to solve a system. I'm going to solve p minus lambda times the identity times v equals the 0 vector for some non-zero v. Such a non-zero v will be an eigenvector with this eigenvalue of 2 plus I. Okay? So I'm going to write down an augmented matrix. The augmented matrix is going to be 1 minus 2 plus I minus 2, 1, 3 minus 2 plus I. And notice my use of parentheses, okay? Very important for good hygiene. Oh, and I can make this an augmented matrix if I want to. But the point that I really want to emphasize is that I know from the calculation that I did for the eigenvalues that the determinant of this matrix with these lambdas stuck in there is 0. And what that tells me is that in this 2 by 2 matrix right here, okay, row 1 is a scalar multiple of row 2. I don't care what the scalar is, but I know that it's some scalar multiple of row 2. So I can use an appropriate scalar multiple of row 1 to kill row 2. In other words, using row reduction, it is totally legitimate for me to write the following. Now I'm going to work out 1 minus 2 plus lambda. I get negative 1 minus I, negative 2, 0, and then 1, well, 0, 0, 0. You feel it? So what this tells me is that if I think about things in terms of v1 and v2, I get that negative 1 minus I parentheses times v1 minus 2v2 is equal to 0. That's the condition on an eigenvector. Now I can move the negative 1 minus I v1 to the other side. And I learned that v1, or negative 2v2, is equal to negative 1, no, I'm sorry, positive 1 v1. Alrighty? So what that tells me is if I let v1 be negative 2, then v2 is 1 plus I. Does that make sense? So an eigenvector is going to be v1 equals negative 2, and then v2 will be 1 plus I. If you don't believe me, shove that v1 and v2 in. This is my v1, And this is my v2. And if you shove those numbers into this equation, you'll see that it works out, because of course it does. All right. So that's my eigenvector, and I'll just remind myself with eigenvalue lambda equals 2 plus I. So then I go back to my ansatz. The ansatz tells me that my complex valued solution, and maybe, I mean, I'm just going to call it X. I could call it Z or something. I don't know, whatever. My ansatz tells me that I need to be looking at -2, 1 plus I, e to the 2 plus I, in parentheses, please, times t. And the problem with this is that this is a complex valued solution. Which is bad, okay? Because what I really want are real valued solutions. So what I'm going to do is manipulate this into its real part and its imaginary part. And the thing that I foie gras down your throat is that the real part and the imaginary part are themselves real valued solutions. And not only that, but they are also linearly independent. Okay, so now I'm just going to do that kind of manipulation on this. First move, I'm going to rewrite e to the 2 plus it as e to the 2t plus, times e to the it. Next thing I'm going to do is use Euler's formula to expand e to the it as cosine t plus I sine t. Nice. Next thing I'm going to do is mash all of this into a single vector. And maybe I'll distribute, actually. So I'll distribute this across. So I get cosine t, and then minus 2 e to the 2t I sine t. Okay. Oh, and then I better leave room because this next one is going to be grosser. Next one is going to be, okay, this one I won't expand out yet. I'll do a little bit of bookkeeping. But hopefully it's clear how that happened. And now I'm going to multiply, and it's a little complicated. I'm going to multiply this 1 plus I with this cosine t I sine t. Okay? And what do I just distribute. Like this, yeah? In the usual way, no big. All right? And if I do that, what I obtain, well, so upstairs stays the same. I'll just leave it like this, okay? I'll deal with that later. But down, and I better leave myself room because I'm going to have 4 different terms here. I'm going to have, so e to the 2t times cosine t plus e to the 2t I sine t. Wow, what am I doing right now? What am I doing to myself? I think this is right. And then plus I e to the 2t cosine t. And then I times I think is negative 1. Well, no, I don't think. I'm pretty sure. I mean, I'm not just pretty sure. I know is negative e to the 2t sine t. Do I really expect you? Yes, to do this? Yes. Now I'm going to segregate the imaginary bits from the real bits. So what are the real bits of this vector? I see one up here, it looks like that. So I get negative 2 e to the 2t cosine t. And what are the imaginary bits of the downstairs? Well, I see 2 of them. There's this bit here, and then there's that bit all the way over there. So I believe I get e to the 2t cosine t minus e to the 2t sine t. And then I'm going to multiply that by I times. Now I look at the imaginary bits. The imaginary bit here is this one. I factor out the I, so what I'm left with is negative 2e to the 2t sine t. And then down here, I've got this bit and that bit there. They both go in the imaginary part. So I have e to the 2t sine t plus e to the 2t cosine t. Okay? So what I've got now is the real part and the imaginary part. And those are themselves real valued solutions. And now I'm ready to write down the general solution. X is equal to C1 times that real part. Oh my God, I'm on an iPad. I'll erase that purple line in a second. Plus C2 times this part. Wait, stop. Plus C2 times this part. I was about to congratulate myself on what an excellent thing this iPad is, but now it's doing all sorts of funny things to me. Style blue. Look at that. Are you proud of me? Well, you can't answer, but you should be proud of me because that's right. All right, now all of this, okay, was to find the exact solution, which we just did. Congratulations to us. But you know what? If all we wanted to know is if the solution looks more like this, or that, okay, we didn't need to do all that work. All we needed to see was the eigenvalue. The eigenvalue is right here. And we see that the A is positive. And what that tells us is that we're in the spiral source category of things with our solution. Wow. And I mean, this is honestly like quite sensible. Because notice that these exponential terms all have positive coefficients. The 2 there. That 2 is the A in the eigenvalue. Okay? And what this is telling us is that this vector is sort of growing larger and larger and larger as t gets larger. So of course we're spiraling away. If that 2 were negative 2, if this was negative 2, here, and there. If that was a negative 2 there, then we would be spiraling in. We'd have exponential decay on x. Okay. That's enough. Bye.